Okay, welcome to today's video everyone. So in this video we're looking at parts 3 and 4 of question 8b from the 2001 HSC exam. Okay, and the previous two parts were done in the previous video, so I suggest you go back and look at that video because we're going to use some of these results in this video. Okay, so let's have a look. Question 3. Suppose that R is a positive rational so that R equals P over Q where P and Q are positive integers. Show that for all integers a and b, either the absolute value of a plus br equals 0, or the absolute value of a plus br is greater than or equal to 1 over q. Okay, and then part 4 says prove that E is irrational. Okay, but let's just have a look at part 3 right now. Okay, so move that away. Part 3. So, we have that R is a positive rational where it says suppose that R is a positive rational. So if it's a rational, it can be written in the form of P over Q, where P and Q are integers. And it tells us that that they're positive integers. So we know that P and Q are positive integers. Okay, and we want to show that for all integers a and b. So, for all a and b that are integers, we want to show that either a plus br equals 0, or absolute value of a plus br is greater than or equal to 1 over q. Okay. So how are we going to do this? Well, it's pretty obvious that we're going to be working with the absolute value of a plus br. So let's write that down and see where we can go from there. So we have the absolute value of a plus br. And now we know what r is. R is p over q. So let's substitute that in for r. So a plus b times p over q. So it's the absolute value of all this. Let's make a common denominator of q. We have AQ plus BP over Q. Okay, and here we have the absolute value of a quotient, and that becomes the quotient of two absolute values. So we're going to have the absolute value of AQ plus BP over the absolute value of Q. Now, one thing that you need to remember, and a lot of people for some reason find this a little bit tricky, but when we have absolute values, you should remember that the absolute value function is defined as a piecewise function, which means the absolute value of x is equal to negative x if x is less than 0, and is equal to x if x is greater than or equal to 0. Okay, so the absolute value of q, well, q is positive. It says so right here. It says in the question that it's a positive rational. So if q is positive, well then the absolute value of q is just going to be q. So we're going to have the absolute value of aq plus bp. Now we don't know whether this is positive or negative, but we do know that q is positive, so we can get rid of these absolute value signs and leave it as just q. Okay. Now why do we do this? Well, we see here that we want a q in the denominator, and this is exactly what we have right here, a q without the absolute value signs in the denominator. Okay, now, there's a couple of things that we need to clear up. We know that a, q, b, and p are all integers. So this is what we can say. Since a, b, p, and q are all integers, then a product and sum of these is also an integer. Now remember, we talked about this in the previous video. This is known as the closure of integers under addition and multiplication. So, if they're all integers, then AQ plus BP is an integer. So we can write it like this. Okay, so any sum and product of integers is going to leave you with an integer. Okay, so if this is an integer, well then its absolute value is certainly an integer, and we can even say that it's a positive integer, because absolute value will make it always positive. So this automatically gives us that the absolute value of this is going to be an integer, but it's going to be a positive integer, because this could take values of -10, and when we take the absolute value, it's going to be +10. If it was 5, the absolute value is going to be 5, and that's still a positive integer. Okay, so the absolute value of this integer, so this is always going to be a positive integer. Okay, so let's have a think about that. What does it mean if it's a positive integer? So therefore, this here can take values of 0, 1, 2, 3, 4, and so on. Now, it's never going to be negative because it's the absolute value, but it can be any of these integers. Okay, so now we need to consider a couple of cases. So the first case that we consider is if it's 0. So if the absolute value of AQ plus BP equals 0, this is what we get. We're going to get the absolute value of A plus BR. Remember, this is what we're trying to work out. So we're going to get this. Well, that's going to be equal to 0 over Q. Okay, so that's equal to 0 over Q, which is equal to 0. Okay, and that's one of the cases that we're trying to prove. So it's either going to be this or this. So this one was probably the easiest to prove, or the easier one to prove. Now, how can we justify this statement? Well, if it's taking any other integer value, then the smallest value it can take is going to be 1. If it was 2, it'd be twice as big. If it was 3, it'd be bigger still, and so on. It'd keep getting bigger for every integer value that you go up by. So if it's 1, then that's going to be the smallest possible value you can take. That's obviously not 0. So this is the trivial case. So in these cases here, so let's just say if this here, this absolute value, that's a P, is non-zero, then the smallest value it can take is 1. Okay, let's get some paper. So, if it's 1, what does that mean? So therefore, this here is greater than or equal to 1. Now, if it's greater than or equal to 1, we can go back up here and claim that this gives us that the absolute value of A plus BR is going to be greater than or equal to, now this here we're saying is greater than or equal to 1, so it's going to be greater than or equal to 1 over Q. Okay? And so we've shown the 2 that we want to show, and we can say QED. Okay, now let's go back and have a look at the question for part 4. It says prove that E is irrational. Now this might seem a bit odd. There's not much information given to you in part 4, but in fact all the information you need you've already worked out in parts 1, 2 and 3. So it says prove E is irrational. Now in part 3 we started off by saying suppose that R is a positive rational. So here we're assuming that R is a positive rational, and if it's a positive rational, then for all integers A and B we have either of these two cases. So if we can assume that E is irrational, and show that one of these two cases don't apply for all integers a and b, then we've proven that E is irrational by a technique known as proof by contradiction. So what proof by contradiction is you start off by assuming something, assuming the opposite of what you want to prove, and then proving a contradictory statement, which then proves that your assumption is wrong, and thus you've proven what you want to prove. So let's go have a go at this one. Prove that E is irrational. Okay, so we can say assume E is irrational. Not irrational, we want to assume it is rational. So assume E is rational. So therefore E can be written in this form, P over Q, where P and Q are integers. And since we know that E are positive, we can say that they're positive integers. Okay. Okay, so what's the next step? Well, we need to sort of look back at the question and see what information we have. Well, here you can see this A plus BR form. Well, it kind of crops up in part 2. We have this A sub n, which is just some integer, so we can think of it as A. So we can have A plus B times E. Now, this is the exact same form as what we have here. So we're going to need to work around this. And you'll also notice that these two integrals, even though this is an n and this is an alpha, they're actually the exact same integral. So, let's see what we can get from that. Alright. So from part 2, this is what we have. We have the integral of from 0 to 1 of x to the n times e to the x dx, and that's equal to a sub n, but that's really just some integer. So we can say a plus b times e, because b is just some integer. Okay, so this is what we have. And also, from part 1, we have that the integral from 0 to 1 of x to the alpha. Now, if I substitute alpha with n, that's not changing the value. It's just a dummy variable. So, if I substitute alpha with n, this is what we get. This is going to be less than 3 over n plus 1. Okay, now that we have this, we can combine these two, and now it should become obvious that this integral, we can now say that this is less than 3 over n plus 1. Okay, we can use this fact and apply it here and say it's less than 3 over n plus 1. Okay, so we can say therefore a plus be is less than 3 over n plus 1. Now, in the previous video, I explained how this integral here is positive, because these two functions are positive over this interval. And I should go back and have a look at that, just so you get a fuller, a more complete understanding of it. But this integral here is always going to be positive, no matter what the value of n is. So then we can also say that this is greater than 0. Okay? So, now we know that this is positive, and we know it's less than 3 over n plus 1. Now, we have this a plus be, which is of the form a plus br, which is what we were working with in part 3. But we want to get the absolute value of this. So let's just have a look at what the absolute value of a plus be would be. So the absolute value of a plus be, if it was less than 3 over n plus 1, what would that be? Well, that's also the same as having the absolute value of a plus be, not the absolute value. You can have it in between 3 over n plus 1 and negative 3 on n plus 1. Okay, so no absolute value sign here. We can just have this in between. Now, this here is a more loose inequality than this. Here, this is a stronger inequality. So, if this is definitely greater than 0, then we can be sure that it's going to be greater than a negative value. So, we can say, therefore, negative 3 over n plus 1 is less than a plus be is less than 3 over n plus 1. This is something that we can be sure of. If this value here is greater than 0, then it's definitely greater than some negative value. Okay, so this is good. Now we can change this up and get it to be this absolute value that we want. So this here is the same thing as the absolute value of a plus be being less than 3 over n plus 1. Okay, so now we're getting closer to what we want. We have this absolute value sign in here. Okay, now let's go back and have a look at what we had. In the question, in part 3, we showed that if r was rational, we would get this equal to 0, or we would get this greater than or equal to 1 over q. So, what we want to show, let's write down what we want to show. We want to show that for some a and b that are integers. Now we don't have to show it for all. If we can show it for some, if we can show it for one a and b, that's enough. But so we can show it for some a and b that are integers, that these two cases, a plus be, the absolute value, is non-zero. And what's the other one? We have to show that it's not greater than or equal to 1 over q, so we need to show that it's less than 1 over q. A plus br is less than 1 over q. Okay. Now, how are we going to do this? Well, let's have a look at this case right here. This less than 1 over q. How are we going to get this less than 1 over q involved in this absolute value thing here? Well, this is where it sort of gets a bit non-trivial. Okay, we can say that for some large enough n, this is what we can say. We can say we can always find an integer n that's large enough so that 3 over n plus 1 is less than 1 over q. No matter how small this 1 over q is, we can always find an n so that 3 over n plus 1 is always less than this. Okay? Now, this large enough is a very loose term, and there is in fact a very formal way of finding what this large enough n could be, but this is not part of our high school work. This involves the precise definition of a limit. But for now, this is sufficient enough for you to say that for some large enough n, we can find an n so that this inequality holds. Okay, so if this inequality holds, well, what does that mean? That means we've pretty much got this. We can now say from here that the absolute value of a plus be is less than 3 over n plus 1, but 3 over n plus 1 is less than 1 over q for large enough n. So we can say that this now is less than 1 over q, okay, for large enough n. And the reason I'm putting large enough n in these inverted commas is because it's not really a technical term, but it will do for now. So for large enough n. So therefore, we have that the absolute value of a plus be is less than 1 over q. So if it's less than 1 over q, we have that it's not greater than or equal to 1 over q. Okay, so we've shown one of these cases to not be true. We've shown this to not be true. Okay, how can we show that it's not 0 now? Let's see. Well, once again, as we said in the previous video, we worked out that this integral here, x to the n e to the x dx, was greater than 0. Okay, and from part 2, we can say, now this was equal to a sub n plus b sub n e, so we can think of a sub n, remember, as any integer, and the same for b sub n, so we can just call them a plus b e. This is greater than 0. Okay, so this here is greater than 0. Now if it's greater than 0, well then it's not equal to 0. So therefore, a plus be is not 0. And if a plus be is not 0, then its absolute value is definitely not 0. So therefore, we have that a plus be is not 0. The absolute value of it is not 0. And so if we call this equation 1, and we call this equation 2, we can then say that from 1 and 2, we have a contradiction. Why do we have a contradiction? Because if E was rational, then this here would be equal to 0, and this here would be greater than or equal to 1 over q. We would have one of these two cases, but we don't. And so from 1 and 2, we have a contradiction. So therefore, our original assumption must be false. Therefore, E is not rational, and finally, therefore E is irrational. Okay, and that's the end of the proof. It's a very nice question. It's definitely a very challenging question, but there are parts in which you can gain marks in these types of questions. Definitely should be able to attempt question 1 and 2. It's not as hard as you think, but you just have to know where to go from, and always look at what the question gives you, because they never give you information for free. Okay, I hope you enjoyed. Thanks for watching.